I'm just going to go over something that's in Education Perfect, but I don't think you guys use some of the information that's there nearly well enough. And this has to do with the rates of change and the fact that some of us are having trouble with what we're actually doing here, with tangents and with the formula, the derivative that we're doing, and so on. So I'm just going to show you some slides that are in Education Perfect and maybe talk over them, that maybe they will help you a little bit with the understanding. So calculus and things that we're doing right now is all about rate of change, right? And the rate of change is just gradient. It's the change in y over the change in x. We've dealt with this for a very long time. The problem is that we're now dealing with rates of change of nonlinear functions, right? So what we need to consider is what's happening to y as x increases. So as we move across x, what is going on with y? So sometimes y is increasing, sometimes it's decreasing, and sometimes it's staying the same. And how fast is it going? Like, is it a change that's fast, slow, or constant? Those are all questions that we ask for rate of change, right? And then we know how that the rate of change for a straight line is a constant, right? And if it's going up, as we move from sort of left to right, it's going up, which means it has a positive rate of change. If you're going left to right and the straight line's going down, that's a negative rate of change because it's a negative slope or a negative gradient. And if it's a horizontal line, it's a zero rate of change. The gradient is zero. The rate of change is zero at that point. There's no change. So that's all with linear functions. And we've all dealt with that for quite some time. But the problem is when the rate of change is not constant and the graph is nonlinear, then what do we do, right? So a positive rate of change will produce a positive graph. Again, as you go from left to right, is the thing increasing? Is it increasing at a steady rate and all that? So, I mean, I know this is increasing because if I drew a tangent at any point, along this, the tangent would be positive, right? If you draw any tangent along this graph, it's increasing. It's increasing over time. Not steady rate of increase, but it's increasing. Whereas this one, as you go from left to right along the x, it's decreasing. That's a decreasing or negative rate of change. Now, if we consider a function that we're familiar with, a polynomial like negative 0.525x squared plus 4, and we graph the parabola, it's an upside down parabola, how would we describe the function and draw the graph when x is greater than 0? So basically, from 0 to 4, this graph is doing something, and we need to be able to describe what it's doing, right? So when x is greater than 5, this graph is decreasing. It's negative. And we see the function is negative because the x increases, y decreases. So we know that as we're going from left to right, as x is increasing, the y is decreasing. That gives us a negative function, our negative function along that area anyway, where x is greater than 0. The graph shows part of the negative parabola in which the slope is negative. Now, let's say we want to find the average rate of change, right? Average rate of change. That's where we use this thing like the secant line, for example. So we have a function that is not constant, and it's curving and so on, and it's changing its rate of change over time. But if we want the average rate of change, then we can just sort of plot a point at 0, 0, and then another point at 168 and 6,250. And we can just do the change in y over the change in x, and we can get an average rate of change, right, which is 37.2 kilometers per hour. So that's the research vessel is traveling at an average rate from 0, 0 to this point here of 37.2 kilometers an hour, right? So that's average speed. So we can also find the average speed of the vessel between 60 and 140, right? So in hours, at hour 60, and at hour 140, again, we draw like a secant line to that curve, and we can get an average speed for that boat at that time, that vessel, which is 25 kilometers an hour. That's its average speed. However, what if we want to know how fast the vessel is traveling at a specific point, right? At a single point, not over an interval of time, but at a specific point. So for doing that, what we were doing earlier is we were drawing a tangent line to a specific point. on the curve. So by sketching a tangent at the point in question, making sure it passes through another point of the graph that is easy to read, we can then calculate the estimated instantaneous rate of change for that point. So all we do is we work out the gradient of that tangent that is hitting the point of 132 and 3500, right? And we need another point to get the gradient, or we can get our calculators to do it. And what it's finding is the gradient of that tangent is 53.5. So at that point, at 132 hours, at that instantaneous moment in time, that vessel is traveling at 53.5 kilometers an hour. And that's by doing a tangent, right? That's what we were doing earlier. However, we can also estimate that instantaneous rate of change using an equation. So another way to travel to Antarctica is by plane. From New Zealand, it takes approximately 8 hours. The elevation of a plane on this flight can be modeled by the following equation. We can estimate how fast the plane is elevating at a specific point by finding the gradient from 2 points just above and just below that specific point. So what we do, now this is not, they're not doing first principle stuff here, right? Okay, so they're not doing our formula. But if we just take the height formula as this parabola and we differentiate that, we use the power rule to differentiate this, then we can figure out what that instantaneous rate of change is. Now, there are other ways to do it, and they use a different formula. There are first principles, there are limits, there's all sorts of things in calculus that you will do next year. But if I just take a snapshot of that slide, if you will, okay? So what we're learning is, okay, I could draw that parabola, right? And I could estimate at a particular point by drawing a tangent what the instantaneous rate of change is for that plane in its pattern and so on, how fast it's going at a particular point, right? So I could find the gradient of that tangent when, you know, at whatever point we're dealing with, right? So we can find that. How fast is that plane traveling when it's starting to come back down to the ground and so on? But instead of doing that, what we're doing is we're learning to do a derivative, which is a formula for a power rule or product rule for being able to find what that instantaneous rate of change is at 5, right? So for this one, if I differentiate it, I'm going to get 0.5 times 2, which is -1. And then the t, it's just t because we go 2 minus the 1, plus 4.6. That's the derivative. Now, if I want to know what the instantaneous rate of change is at that point for the plane, then I simply throw the 5 in, and I figure it out, right? I work it out. And so that value, that -5 plus 4.6, which is -0.4, that is, and if it's kilometers per hour or whatever the units of is, at that point, that plane is traveling at 0.4 kilometers per hour, or whatever the units are. I'm making it up now, right? That's what we're looking at, and that's what a derivative basically does.